Hello everyone and welcome to today's presentation. I am Dr. S.K. Singh and I'm pleased to have you here. Today we will be discussing the qualification of analytical balances. This is the first slide, so I'd like to start by giving you a quick overview of what to expect. We'll cover the importance of analytical balances, their key features, and how to ensure their proper qualification. I look forward to sharing this information with you. Let's get started. Now, let's look at the three major phases involved in qualification. First, we have IQ, which stands for Installation Qualification. This phase ensures that all equipment and systems are installed correctly and according to specifications. Next is OQ, or Operational Qualification, where we verify that the equipment operates as intended under normal conditions. Finally, we have PQ, or Performance Qualification, which confirms that the system performs effectively and consistently in real-world conditions. To visualize this process, there's a flow diagram that goes from install to verify, then test, and finally document. This flow highlights the step-by-step approach we follow to ensure everything is properly qualified and documented. Understanding these phases is crucial because they form the backbone of our qualification process. They help us ensure that our equipment is reliable, compliant, and ready for operation, which ties directly into our overall goal of maintaining quality and consistency throughout our processes. All right, let's start by talking about checks. First, we need to verify the balance model and ensure that the serial number matches what's documented. This step is crucial to confirm we're working with the correct equipment. Next, we look at the power supply and grounding, making sure the power source is consistent and the grounding is properly connected to prevent any electrical issues. Then, we focus on leveling and environmental controls. It's important to check that the equipment is properly leveled and that environmental factors like draft and vibration are minimized, as these can impact performance. Lastly, we review the certificates of calibration and conformance to ensure the equipment has been properly calibrated and meets all required standards. Moving on to documentation, we gather the IQ checklist and photographs. These serve as essential proof that everything was set up correctly and according to plan. Now, talking about the installation qualification, or IQ, this is where we document and verify that the installation process was completed properly. It's about making sure everything is in the right place, correctly connected, and ready for operation. This careful validation helps us ensure the integrity of the equipment right from the start, setting the foundation for reliable performance throughout its life cycle. Now, let's take a closer look at operational qualification, or OQ, and the tests involved in this phase. First up is linearity. This test ensures that our equipment provides accurate measurements across the entire range we plan to use it. It's crucial because we want to be confident that the instrument's responses are proportional to the actual weights or signals. Next, we have repeatability. This means checking that the device gives consistent results when we perform the same measurement multiple times under the same conditions. Consistency here is key to reliable operation. Then, there's sensitivity, which involves determining the minimum weight the instrument can detect and still produce a readable, accurate result. This helps us understand the limits of our equipment's performance. Finally, we evaluate the response to change. This test confirms that the instrument responds appropriately when conditions change, such as variations in temperature or load, ensuring stability and accuracy under different scenarios. All these tests are performed using certified calibration weights that are traceable to national standards. This traceability is fundamental because it guarantees that our calibration is accurate and universally recognized. In the context of overall quality assurance, these tests and standards help us verify that our equipment is functioning correctly and reliably before we move on to subsequent qualification phases. Let's take a closer look at the error measurements. For example, when we have a 1 gram weight, the error is about plus 0.3 milligrams. If we move up to a 5 gram weight, the error increases slightly to around plus 0.7 milligrams. And for 10 grams, the error is approximately plus 10 milligrams. These numbers highlight how measurement errors can vary depending on the weight we're measuring. It's important to understand that within our process, we accept measurements that fall within the acceptable range, which is typically within plus or minus 1 standard deviation of the tolerance. Now, let's connect this to the concept of linearity in our quality control tests. For our OQ, or operational qualification, we often use a linearity example to verify that our measurement system maintains accuracy across different weights. The procedure involves measuring standard weights, like 1 gram, 5 grams, and 10 grams, and recording the data. This helps us see how well our measurement system performs across a range of values, ensuring consistency and reliability in our measurements. Let's walk through this repeatability example to understand how consistent our measurements are. First, we perform a procedure, which in this case is weighing 1 gram 10 times. The measurements we obtained are 0.9997, 1, 1.0002, 0.9999, 1.0001, and so on. Next, we calculate the mean, or average, of these measurements. In this example, the mean comes out to 1 grams. We also calculate the standard deviation, which measures how much the individual measurements vary from that mean. Here, the standard deviation is 0.00017 grams. Then, we determine the percentage relative standard deviation, or percent RSD. This is done by dividing the standard deviation by the mean and multiplying by 100. So, 0.00017 divided by 1 times 100 gives us 0.017%. Now, what does this tell us? For repeatability, we look at whether this percent RSD is within acceptable limits. Typically, for this kind of measurement, an percent RSD of less than or equal to 0.1% is considered a pass. Since our calculated value is only 0.017%, it falls well within the acceptable range, indicating good repeatability. This example highlights the importance of assessing repeatability to ensure our measurements are consistent and reliable, which ties into the overall theme of quality control and method validation. Let's talk about the concept of minimum weight in the context of sensitivity and precision. Essentially, the minimum weight is the smallest amount of a standard that we can weigh and still achieve a specific percentage of relative standard deviation, or percent RSD, which is often set at 0.1% or less. This is crucial because it tells us the limit of our method's sensitivity, how little we can accurately measure. Now, the procedure to determine this involves weighing decreasing amounts of the standard until we notice that the RSD starts to increase beyond our acceptable threshold. In other words, we keep reducing the weight until our measurements become less consistent, indicating we've hit the lower limit of reliable detection. And finally, the acceptance criterion here is to report the minimum weight at which we can still achieve that acceptable precision. This ensures that we're working within a reliable range, maintaining confidence in the results, and connecting this to the overall goal of ensuring our analytical methods are both sensitive and precise. Let's talk about measurement uncertainty. So, what exactly is uncertainty? Well, it's essentially an estimate of the doubt that surrounds any measurement we make. No measurement is perfectly exact, and this doubt helps us understand how reliable or precise our results are. This concept isn't just academic. It's actually required by standards like ISO IEC 17025 and is referenced by USB, especially when we're dealing with critical measurements where accuracy is paramount. Now, when we think about uncertainty, it can come in different forms. The two main types are systematic errors, also known as bias, and random errors, which relate to repeatability. Systematic errors are consistent and can skew results in a particular direction, while random errors fluctuate and can cause variability between measurements. Understanding these types helps us assess and manage the overall uncertainty in our measurements, which is a key part of ensuring quality and compliance throughout our processes. Now, let's take a closer look at the components involved in uncertainty calculation. This is a crucial part of our analysis because understanding and quantifying uncertainty helps us make more informed decisions. When we talk about uncertainty calculation, we're essentially trying to measure how much variability or unpredictability exists in our data or model. This involves identifying the key factors that contribute to uncertainty, such as measurement errors, model assumptions, or data variability. By accurately calculating these uncertainties, we can better assess the reliability of our results. Remember, the goal here is to not just acknowledge that uncertainty exists, but to quantify it precisely so we can account for it in our overall analysis. This step ties directly back to our overarching theme of improving accuracy and confidence in our findings. When we look at the calibration standard uncertainty, we're talking about 0.00015 grams. This value reflects how precise our calibration process is and helps us understand the potential variation in our measurements. Next, we have the repeatability standard deviation, which is 0.00017 grams. This tells us about the consistency of our measurements when we repeat the same process under the same conditions. Moving on to resolution, our instrument can detect changes as small as 0.0001 grams. To incorporate this into our uncertainty, we divide that by the square root of 12, which gives us approximately 0.0000289 grams. This step accounts for the variability associated with the resolution of the instrument. Finally, there's the environmental factor, which adds another 0.00008 grams to our overall uncertainty. This accounts for external influences like temperature, humidity, or vibrations that could slightly affect our measurements. Putting all of this together helps us understand the total measurement uncertainty, ensuring we know how reliable our results are and where we might need to improve. Let's take a closer look at expanded uncertainty. This concept is really about understanding the range within which the true value is likely to fall, considering all potential sources of error. It's more comprehensive than just a simple measurement error, because it accounts for various factors that can influence the accuracy of our results. When we talk about expanded uncertainty, we're essentially scaling up the combined uncertainty with a coverage factor, often 2, to give us a wider interval that we can be more confident about. This helps us communicate how reliable our measurements are, which is crucial in fields where precision matters a lot. By thoroughly evaluating and reporting expanded uncertainty, we ensure that the data we present is transparent and trustworthy. And remember, understanding and properly calculating expanded uncertainty ties back into the overall goal of ensuring measurement quality and consistency. Now, let's talk about performance qualification, or PQ, which is all about evaluation under routine conditions. Essentially, this means using typical samples like tablets or powders that we normally work with. The goal here is to assess how accurate and precise our methods are when applied in the real workflow, not just in controlled lab settings. For example, you might weigh out 10 replicate samples and then calculate the mean and the relative standard deviation, or RSD. This helps us see how consistent our measurements are across multiple samples. It's also important to document any trending you observe over time. This way, we can monitor the ongoing performance of our methods and ensure they remain reliable and accurate during routine operations. Overall, PQ is a critical step in confirming that our processes work effectively in everyday scenarios, supporting the overall quality and integrity of our results. Let's talk about documentation and compliance. First, there are the required documents we need to have in place, such as IQ, OQ, and PQ protocols and reports. These are essential for showing that our equipment is installed, operated, and performing as intended. Next, we need calibration certificates, especially for traceable weights, to ensure our measurements are accurate. It's also important to have uncertainty calculation worksheets. They help us understand the level of confidence in our measurements. And finally, trend and control charts are vital tools for monitoring our processes over time and identifying any deviations early on. Moving on to audit readiness, It's crucial that any deviations are thoroughly documented, so we have a clear record of what happened and how it was addressed. Corrective actions must also be recorded meticulously. They show that we're taking appropriate steps to fix issues and prevent recurrence. Overall, these elements are all about maintaining a solid documentation system that demonstrates our compliance and readiness for audits. It's about being proactive, organized, and transparent, key factors in ensuring continuous quality and regulatory compliance. Let's wrap up with some key takeaways. First, qualification is essential because it ensures the reliability of your weighing data. When your equipment is properly qualified, you can trust that the measurements are accurate and consistent. Next, it's important to remember that all these processes must meet USB and other regulatory requirements to stay compliant and ensure product quality. When we talk about operational qualification and performance qualification, or OQ and PQ, these include specific quantitative tests. These tests help verify that the equipment performs as intended under actual working conditions. Adding an uncertainty calculation into your process is a critical step, as it provides an added layer of confidence in your measurements. It helps you understand the possible margin of error and ensures your data is robust. Finally, maintaining complete and accurate records throughout this process is vital. Proper documentation supports compliance, enables traceability, and helps in troubleshooting if any issues arise. In essence, these points come together to form a comprehensive approach to ensuring your weighing processes are reliable, compliant, and scientifically sound. Let's take a moment to look at some key references that underpin our quality and compliance efforts. First, USP 41 and 1251 provide essential guidance on weighing and balances, emphasizing the importance of accuracy and reliability in our measurements. Then, there's 21 CFR Part 211, 160b, which focuses on the calibration of equipment, highlighting that regular calibration is vital to ensure our instruments are functioning properly and producing valid results. Additionally, ISO IEC 17025 sets the standard for measurement uncertainty requirements, reminding us that understanding and minimizing uncertainty is crucial for credible data. Moving on to the key principles that support these standards: traceability, calibration, and documented evidence. Traceability links our measurements back to a recognized standard, ensuring consistency and confidence in our results. Calibration is the process of adjusting and verifying our instruments to maintain their accuracy over time. And finally, documented evidence is the backbone of our compliance, keeping records that prove we've followed the correct procedures and standards. All of these elements work together to maintain the integrity of our measurement systems, supporting the overall quality and compliance of our operations. For further support, please don't hesitate to reach out to me. I'm here to help with any questions or additional assistance you might need. And with that, I want to thank you all for your time and attention today. I hope you found this presentation valuable and insightful. Remember, the key points we've discussed are designed to empower you and help you succeed. So if anything comes up later, just get in touch. Thanks again, and I look forward to connecting with you soon.